I am Daniel Mendes, and I will be presenting our paper entitled Collaborative Tabletops for Blind People, the Effect of Auditory Design on Workspace Awareness. Tabletops have significant advantages in supporting multi-user interaction, namely due to their large shared surface. Also, tabletop geometry has been shown to encourage equitable participation among users, as well as simultaneous individual interactions with the digital content. Previous research highlighted several benefits of using interactive tabletops, such as improving collaborative learning, enhancing social interaction, and fostering creativity and engagement, among others. However, people with visual impairments can struggle to engage with such large surfaces. We argue that not being able to use interactive tabletops and participate in these group activities, for example due to visual impairments, can be a vehicle of social exclusion. Despite being an inherently visual technology, touchscreen devices can be used by blind users. Screen readers, such as Apple's VoiceOver or Android's TalkBack, allow users to explore and control the device by providing audio feedback for touch actions. However, when considering the spatial awareness of interface elements, these accessibility services are mostly designed for smaller form factors, rather than large collaborative surfaces where the ability to locate items and establish relationships between them is more challenging. Examples of applications for such devices include exploring maps and anatomic models in educational settings, or mind maps in brainstorming sessions. In these, the ability to locate artifacts without losing spatial awareness and to relate them is relevant. While there is a large body of work on touchscreen accessibility, research has been restricted to single-user interaction. This raises the question of how accessibility services can support non-visual collaborative activities on large touchscreen devices. Namely, how can we inform users about the actions of others? This notion of monitoring the activity of others, which provides context for one's activities, is defined as workspace awareness, which is a crucial aspect of collaboration and often relies on visual display techniques. However, little is known about using audio for tabletop multi-user interaction, particularly on how to provide workspace awareness and support blind people in joint activities. In this work, we present a study that contributes to the understanding of auditory design in enabling non-visual collaboration in large touchscreen surfaces. Our main goal was to understand how the amount of auditory information affects both information exchange about task workspace awareness and task performance. To this end, we designed and implemented a non-visual tabletop prototype that can be customized to provide different auditory feedback modes. It consists of an interactive tabletop, two Bluetooth stereo headphones, and a pair of depth cameras. It provides users with a unique text-to-speech voice to support collaboration. Each user is assigned a different voice, either male or female, as audio frequency is a good parameter to maximize speech discrimination. Furthermore, we use specialized speech to display target positions on the tabletop. In terms of collaborative work, the specialized feedback implicitly illustrates the screen areas being explored by partners, thus increasing the potential to increase workspace awareness. We investigated 3 auditory feedback modes, which employ different trade-offs between privacy and visibility of the user's information. Private behaves similarly to a traditional screen reader, as speech feedback is restricted to users' own actions. In the public, users receive audio feedback about their own actions as well as the actions of partners. For the task dependent, in addition to their own actions, users receive feedback about their partner's actions that are relevant for the collaborative task. Since tabletops excel in conveying 2D spatial relations, we chose the fundamental task of exploring the screen and selecting targets. We had 3 types of targets: squares, circles, and triangles. We asked participants to select all squares and circles. Triangles were distractors and simulated irrelevant interface elements. A participant could only select either squares or circles. Participants were given a maximum of 7 and 5 minutes to complete the tasks with distractors and without distractors, respectively. We recruited 10 participants in 5 pairs. They were recruited from a local social institution, and their ages ranged from 20 to 59 years old. All were legally blind and had daily experience with touchscreen mobile phones, and consequently had experience with VoiceOver or TalkBack. None had previous experience with tabletop displays. Regarding task performance, all pairs successfully completed all tasks within the time limit. The statistical analysis of task completion time revealed no significant differences between conditions, suggesting that although public mode delivers irrelevant auditory information, users can filter it out and maintain task efficiency. Regarding workspace awareness information exchanges, we did not find a significant main effect of either feedback mode or distractors. However, we did find a significant interaction between factors, suggesting that the public feedback mode is more sensitive to distractors than the private mode, increasing the total information exchanges. Also, participants supplied significantly more information to each other than requested in the private and public conditions. We also registered examples of collocated non-visual collaboration behaviors, namely how workspace awareness information was both supplied and extracted, and how participants coordinated strategies. Participants often supplied relevant target location information to their partners as soon as they found it and used various nonverbal behaviors that supplemented verbal instructions. These included deictic references, audible tapping on the tabletop, leaving the finger as a reference point, and retrieving the partner's hands. To retrieve location information, participants used two main strategies. They either reacted to the spatialized feedback or offered their hands so that their partner could guide them. Regarding coordinating strategies, only one pair prearranged a strategy to find all targets efficiently. The strategy was based on divide and conquer. The remaining strategies emerged from individual behaviors. Individualists adopted the strategy of prioritizing selecting their own targets, and an over-helper participant opted for sharing all information without much care for its relevance, which sometimes seemed to have a negative effect on the partner. There were also physical information exchanges. Physical contact was widely advantageous to exchange information about target location and complement deictic references. However, we also observed several cases where participant screen exploration resulted in unintentional physical contact, which can encompass negative consequences. Based on our results and observations, we were able to devise a set of implications that can be useful for interaction designers targeting multi-user screen readers, particularly for tabletop interaction. So, there should be a focus on information sensitivity, reducing on-screen content, considering interaction on and above the tabletop, providing awareness about the other user, making deictic expressions meaningful, and using multiple taps wisely. So this concludes our presentation. Thank you very much for your attention.